Once all the parameters of the structure have been defined, we can now move on to defining the structural model and also try to highlight some of the most frequent modeling problems. From the 3D environment, we can of course access the structural view, which can also be accessed using this button located at the top of the window. In general, to execute the calculation while in structural view, you'll need to perform the first phase of the structural model and floor plans calculation. Once the first phase of the calculation is completed, the structural model is defined. Considering that we can see the 2D elements, such as the walls and foundation slabs, which are represented by shell elements. Here's the model that the program automatically generates starting from the architectural model as defined previously. Here's the 3D model, defined from the various elements. Notice the BIM schematization of one-dimensional elements, while the two-dimensional elements are represented by triangular elements. The nodes are represented by infinitely rigid zones, and this is the model that is sent to the finite element calculation engine. In general, during the model definition, it becomes clear that the structural engineer can intervene, for example by selecting the walls or the foundation slab. For each of these elements, the structural engineer can define the HP shell step to define the structure grade. One of the most fundamental aspects in the definition of a model is those related to internal and external links. If we select a foundation node in its properties, you have its characteristics, the type of external constraint, in this case, Winkler. You can see that the program has automatically defined the external constraints for the foundation nodes, clearly showing the displacement stiffness and rotation in the X, Y, and Z plane stiffness values, to which this constraint is exposed. If instead, we select a node from a higher plane, we can notice that the node is free, because unless it is in particular situations in which the nodes are locked, in general, the nodes in position are free to move. However, in the architectural view, if we select an element, such as a beam, you can see that the Properties toolbox on the right provides a series of options to define the internal constraints. To define the related displacements, it is necessary to define the internal constraints at both ends of the axis. To understand where the beginning and where the end of the beam is, simply look at the arrow symbol on the element. This points to the end. The S letter found at the beginning of a selected beam shows the constraint displacement and rotation. In the case of reinforced concrete structures, we know that the condition of continuity is the rule, so this condition of the constraint is fine. But if this beam is a steel or timber beam, it may be necessary to change the condition of the start and end constraints. If we choose a supporting condition both at the beginning and at the end, these N letters allow us to understand that the program has cancelled the rotation stiffness at the lengths of the axes marked as 2 and 3. It is also possible to view the element's local axis reference. From the 3D editor menu in the local axis, let's activate the Add option. Showing therefore axes 1, 2, and 3. Once the internal constraints have been defined, while in the structural environment, we can activate a summary view of the internal constraints. In fact, here we have the Internal Constraints button. By activating it, we have the graphical representations that help us to quickly identify for which unions the internal constraints have been modified. In particular, if we consider the component on axis 1, the red arrows specify that we have a 100% degree of constraint. But if we choose a displacement component, for example the rotation along axis 3, the blue arrows, in correspondence with the beam, on which we have modified the internal constraint. The chromatic scale allows us to understand that we have cancelled the rigidity along axis 3. These visualizations are useful if we imagine, for example, a steel structure, for which we need to modify the internal constraints. These visualizations allow us to check modeling errors, thanks to a graphical representation of the rings correctly modified. As usual, with the definition of the structural model, one of the most common problems is related to the behavior of the floor's slabs at levels. For the management of the modeling of the floor's slabs or rigid floors is necessary to go to the Levels Management section. In the management of the levels on each plane, it is possible to activate the rigid behavior with a simple click. By activating the field, we assume that all the forging or panel is rigid. Then the program defines the classic kinematic relationship between the main node and the secondary nodes of the floor. Not always, this modeling hypothesis is the most appropriate, in which case you need to deactivate the field. Just look at the model in which we have a series of openings on a floor such as at the stairs. So it is not always the solution the rigid floor is the right one. The alternative consists in giving the rigidity, not to the whole floor but to a single floor. If we select the floor object, on the right, in the toolbox of the properties we find within the characteristics the sublevel stiffness, so we can impose an infinitely rigid behavior on this floor. From a model point of view, in the presence of this information, the program introduces a series of connecting rods. Those are elements with high axial rigidity to prevent the relative movements between the nodes that belong to this floor. Another critical aspect of modeling is the stair object. A common error in modeling this element causes structural problems. Let's look at the case with an example. We open a file where we have modeled a simple structure, which supports a series of scales of different types. As a type of slab inclined, beam embedded to the left and beam recessed to the right, the first thing is to observe the structural model, since the view of the structural model helps us to quickly understand if these stairs are well connected and to the structure. In this example, we left these ramps without generating it. If we just save the drawing, it seems that everything works correctly. We have the first stretch and in continuity we have the second stretch. Observing the architectural model, it seems that everything is connected correctly. But if we generate the structure of these ramps and quickly consult the structural view, we quickly see that this stair is not in structural continuity. We see this because in the structural view we lose sight of the elements by viewing only the structure. So for stair we will simply have a connection that passes through the center of gravity of the structural element. As for the second part of the staircase, we see that it is a recessed beam on the right, so the stairs and the landing are simply loaded on the shelf or the recessed, so in the structural model we only see the diagram. We can assume that this stair has no structural continuity and therefore is not correct. To create this continuity, it is necessary to reset the structure of the stair. So, access the properties of the element and add a landing. In this way we create a penetration with the rest of the other ramp. When we generate the structure of this stair, we can verify that it has a structural continuity. So for stair we will simply have a connection that passes through the center of gravity of the structural element. As for the second part of the staircase, we see that it is a recessed beam on the right, so the stairs and the landing are simply loaded on the shelf or the knee beam,